Hello, my name is Bahit Anurashevna Alipova, and I'm Associate Professor at the International Information Technology University. I'm continuing my lesson in framework of course methods of nonlinear programming, and this is a lesson about additional methods. I'm using open source slides of Professor Dmitry Bertsekas from MIT. So actually, I have improved a little bit these slides, but following the main direction. Today, I would like to tell in framework of this lecture outline about least square problems and incremental gradient methods, conjugate direction methods, quasi-Newton methods, coordinate descent methods, and recalling by this least square problem. Just to remind you the concept of least square problems, you can see here some drawing. So we have like set of empirical experimental data, and the least square problems result give us the main trend of all this set. So this is a lecture outline for today, and we will continue. Incremental gradient methods. At first, would like to remind you a steepest descent method. It involves evaluating the entire gradient, making it computationally expensive for large dataset or systems. And we can see the difference between incremental gradient methods, in which components of the least square functions will be calculated by processing one component of the gradient and time, instead of evaluating the full gradient. It's particularly useful for large-scale problems where calculating the full gradient is expensive. Here, the method sequentially refines the estimate Xi by using one gradient component at time, leading to an efficient incremental approach. Here in the draw, you can see advantage of incrementalism, and the plot demonstrates how incremental methods work. Each curve represents a subproblem or component, where the goal is to minimize the sum of these quadratic terms. Incremental methods handle one component at a time, moving closer to the solution with each step. The solution minimizes the overall quadratic objective, represented as a minimum of the sum of the individual terms. And the approach avoids the need to compute the full gradient, saving computation time and memory, especially for large-scale problems. On this slide, we will consider gradient methods without errors. And here we can write incremental gradient methods as main typical iteration form. And here the first term, this is the main gradient update. It follows the classical gradient descent rule, where each step moves in the direction of the negative gradient of the function. And summation indicates that the update considers multiple component functions, gi of x, making it suitable for decomposable optimization problems. And error term corrects the gradient estimation by adjusting for previous iterates, xi minus 1. It helps in stabilizing the updates and reducing variance. This incremental update allows faster convergence compared to standard gradient descent. Error terms is proportional to step size alpha k, and meaning smaller step size leads to smaller errors. If alpha k is too large, errors might accumulate and leads to instability. Convergence conditions. The method generally converges when the step size alpha diminishes over time. And I can add here that convergence is ensured under a Lipschitz continuity assumptions on gradient, meaning that the gradient does not change too abruptly. I will remind you a Lipschitz condition next slide. But now about effect of a constant step size alpha. If alpha k remains constant, the algorithm does not converge exactly. Instead, it oscillates around the optimal solution within a small neighborhood. This means that with a fixed step size, we can obtain an approximate solution but not the exact one. So in this case, the size of alpha k is quite crucial. Practical applications for large-scale optimization. This method is useful for problems where computing the full gradient is expensive. For machine learning, used in stochastic optimization where data is processed in small batches instead of full gradients, and in convex optimization problems. This method is effective in structured problems where subfunctions can be optimized incrementally. So summarize, I can tell that the incremental gradient methods update the variable xk using component-wise gradients. It includes an error correction term to improve stability, and convergence is guaranteed for diminishing step size, but for constant step size, it converges only to a neighborhood of the solution. To remind you Lipschitz condition on the gradient, if the gradient is Lipschitz continuous, the function does not have sharp turns or discontinuous. And this condition is crucial for ensuring gradient descent methods converge properly. The Lipschitz conditions ensure that the functions, or its gradient here does not change too abruptly. In gradient descent, this condition helps set a proper learning rate alpha for convergence. Many real-world problems such as logistic regression, deep learning, and economic modeling rely on Lipschitz conditions function for stability. So by summarizing why use one component gradient at a time, it means actually we would like to use the computational efficiency as much as possible, and allows us to be flexible and for better convergence in some cases. Let's consider conjugate direction methods. Objective of the method I can express like faster convergence without Newton's method. Steepest descent can be slow, especially for ill-conditioned problems. Newton's method offers faster convergence but requires computing the Hessian matrix, which is computationally expensive. In its turn, conjugate direction methods provide an efficient alternative, particularly for quadratic models. And here we are representing a quadratic function f of x, in which x is the vector of variables to be optimized. Q is n by n positive definite matrix ensuring a unique minimum, and B is n-dimensional vectors transposed here. So in Many optimization problems, particularly in least squared regression and numerical linear algebra, can be expressed in this form. So if Q is diagonal, the problem is simple, but for general Q, we need efficient algorithms like conjugate gradient methods. The method guarantees that only n iterations are needed to minimize function if we use conjugate directions instead of arbitrary descent directions. A set of direction, I mean d1 and so on dk, for all I is not equal j, are mutually independent in transformed space defined by Q. So they would be like a Q conjugate. In steepest descent, successive search directions are often aligned, leading to slow convergence. Conjugate directions avoid this issue, ensuring that progress is made independently in each direction. Generic conjugate direction methods are representing here the iteration in which dk is conjugate search direction. Alpha k is step size obtained through line minimization, in which alpha k is the argument from minimum of alpha k xk plus alpha k dk. This means that in each iteration, we move in the optimal step size along the conjugate direction. Application beyond quadratic problems, also initially developed for quadratic functions, conjugate direction methods also work for non-quadratic functions, which is, could be quite useful for us for next calculation. When applied near a non-singular local minimum, the method behaves similarly and provides faster convergence than steepest descent. Here on this picture you can see expanding subspace theorem. I'm giving here without any proof, and the left diagram represents the search direction in an uncorrected space. While the right diagram shows the transformed search direction using preconditioning, if you can see here. Let's consider several forms of different matrix Q, which for sure should be symmetric positive defined matrix. And we can consider here that different forms of matrix Q influence the behavior of optimization algorithms like steepest descent, conjugate gradient methods, and Newton methods. For sure that we can split them like for well conditioned, ill conditioned, and maybe like a general case. And this identity matrix, diagonal matrix, symmetric positive definite matrix. Another form of matrix Q could be in form of sparse matrix for large-scale problems, nearly singular matrix, poorly conditioning, and Hessian matrix from a quadratic functions. In each case, you can see which matrix could be often arises in different problems, and for sure which problems could be raised here, and which solvers, for example, like conjugate gradient or GMRS, performs well or not in each unique case. So now we can little bit like finalize that the form of the matrix Q can have some influence on the form of the finding of our function, quadratic function, And for sure, well-conditioning matrices, for example, identity matrix, make optimization fast. Ill-conditioning slow down gradient-based methods. And sparse matrices are computationally efficient for large-scale problems. And for sure, nearly singular and singular are problematic and require preconditioning. Let's consider how to construct a set of Q conjugate directions from a given set of linearly independent vectors using a modified Gram-Schmidt procedure. In optimization and numerical linear algebra, when solving a quadratic minimization problems for function f, where Q is symmetric positive definite matrix, conjugate the gradient methods require a set of conjugate directions. It's here like d0 and so on dk, such that this multiplication as diq dj should be equal 0 for any I and j does not equal. And this ensures that fast convergence, then it means that faster convergence than steepest descent, and avoids redundant search directions, since we typically start with a set of linearly independent vector xi, xi0 and so on xk. We need to wait to construct an equivalent set of Q conjugate directions. How to construct such kind of Q conjugate directions? At first, we are given a linearly independent set of vectors xi0 and so on xk. We can construct a corresponding set of Q conjugate directions d0 and so on dk, and while we would be ensured this sum of multiplication of step size and corresponding directions is equal of multiplication of for sure step size and our linearly independent vectors xi. We start the Gram-Schmidt procedure. Start with we initialize our first search direction as d0 is equal xi0. Since this is the first direction, it does not need any modification. And using Gram-Schmidt orthogonalization to make the direction Q conjugate Q conjugate, and for subsequent directions we express di plus 1 as the sum of linear combination of the new independent vector xi plus 1 and the previous conjugate direction. Let's consider here how conjugate gradient methods, how the search directions are generated using the Gram-Schmidt process. The method is used for solving quadratic optimization problems efficiently, particularly when dealing with large-scale symmetric positive definite systems. Using Gram-Schmidt theory, Gram-Schmidt procedure to generate conjugate directions, the search directions in this method are constructed by applying the Gram-Schmidt orthogonalization process to the negative gradient. I mean here xk is equal to negative gradient of cost function at iteration k starting from 0 till n-1. Then we can find the search direction dk is constructed such that each new direction is Q conjugated to the previous one. Using the Gram-Schmidt process, the search direction dk are given by such kind of formula in which minus gk, this is gradient of the cost function. Here is minus gk is a new steepest descent direction, and the summation term removes any components that are not conjugate, ensuring that dk remains a q orthogonal direction. This approach avoids the zigzag behavior of steepest descent, leading to faster convergence. Key fact here is that the direction formula can be simplified. Instead of computing a full Gram-Schmidt correction term, we can recursively define the new search direction dk as a new direction where the first term is negative gradient and the second term determines how much of the previous direction should be retained. This is a crucial result that significantly reduces computational complexity, making the conjugate gradient method practical for large-scale systems. Computing the scalar b the parameter is computed using one of the following formulas. One could be Fletcher-Reeves formula or Pollack-Rabier formula. We are having here just two choices, but it could be much more. And interpretation of bk. If bk is equal 0, the method reduces to steepest descent. If is not equal 0, we combine the previous search direction dk minus 1 to maintain conjugacy. And a Fletcher-Reeves formula ensures convergence for convex problems. It's easier to compute. And Pollack-Rabier formula works better in practice for non-quadratic functions and adapts the search direction dynamically. Termination of the method. The conjugate gradient method terminates after at most n steps. And in n-dimensional space, at most n mutually conjugate directions can be formed. And after n steps, the exact solution is found in exact arithmetic, assuming no round of errors. For large systems, conjugate gradient methods provide a huge advantage since it can approximate solutions much faster than direct methods, for example, like Gaussian elimination. And it could be applicable to non-quadratic problems. Originally, this method designed for quadratic functions, but however, it can be extended to general nonlinear problems using nonlinear conjugate gradient methods, where the function is not quadratic, but the same update rule is used, and the gradient gk is recomputed at each steps. In machine learning, physics and engineering and many optimization problems are not perfectly quadratic, and modifying conjugate gradient methods with line searches allows it to work for general nonlinear functions. Now let's proof of conjugate gradient result and explain why the gradient gk in the conjugate gradient methods are linearly independent until termination. The argument is proven using mathematical induction and the expanding subspace theorem. The conjugate gradient methods generate a sequence of gradients G0, G1, and so on, Gk. These gradients must remain linearly independent until the method converges to the solution. The proof uses induction to show that all gradients remain linearly independent until the termination condition gk is equal 0 reached. Okay. When k is equal 1 for the first step, we only have one gradient g0, which is trivially linearly independent. Inductive hypothesis assume no termination after k steps. So assume that after k steps, the gradient g0 and so on gk1, gk minus 1 are linearly independent. This means that the corresponding search direction, I mean d1, d0, d1 and so on dk minus 1, also span the same space at this gradient. So actually span d0 and so on dk1 minus 1 is equal span of our gradients. Don't forget, this is the meaning of the span. Now we need to prove that the next gradient gk, I mean in this sequence, is also independent. Now we have two possible cases at step k. The first step, if gk is equal 0, this means that the gradient has vanished and we have reached the exact solution. The algorithm stops, meaning no further steps are required. In the case 2, in which gradient is not equal 0, we continue the iteration, and in this case gk is non-zero, but the expanding subspace property, the new gradient gk is orthogonal to all previous search direction, to d1, d0 and so on dk minus 1, and additionally, due to conjugacy property, gk is also orthogonal to all previous gradients, g0 and so on gk minus 1. So gk is linearly independent to all previous gradients, and it must be linearly independent of them. This completes the induction step, proving that all independent until termination. Maximum of n independent gradients, we can tell about that since the search space has at most n dimension for n by n system, we can generate at most n linearly independent gradients. Therefore, the algorithm must terminate at some steps k less or equal n, meaning that at some step gk is equal 0, indicating convergence. Summarizing, induction proves that all gradients gk remain linearly independent until termination. The expanding subspace theorem ensures that each new gradient is orthogonal to the previous one. Since at most n linearly independent gradients exist, conjugate gradient method must terminate in at most n steps. And final steps, where gk is equal 0, confirms that method has found the optimal solutions. This slide discusses quasi-Newton methods, which are optimization techniques that approximate the inverse Hessian matrix to efficiently solve unconstrained optimization problems. The most famous of this method is BFGS, Broyden-Fletcher-Goldfarb-Chanot method. We will consider this here, some kind of this. The general update rule, this iteration formula for updating the solution is xk plus 1 is equal xk minus alpha k dk and gradient of cost function f of xk. And here xk is the current estimate of the solution, alpha k is the step size typically determined by line search, dk is an approximation of the inverse Hessian matrix, and nabla f is the gradient of the function at xk. Instead of computing the Hessian matrix nabla squared f explicitly, which is computationally expensive, quasi-Newton methods construct an approximation iteratively. The key idea of quasi-Newton methods is that the differences between successive iterates and gradients provide curvature information about the function. The curvature condition is approximated as Q is Hessian multiplied by pk, whereas pk represents the step taken from xk to xk plus 1, and qk, this is the difference between two gradients of the function, the change in gradient. So the Hessian here approximated here as a subtraction of vector q and vector p. This relationship captures how the gradient changes in response to a step pk, allowing us to approximate second-order curvature information. The quasi-method update formula, just to remind you, Broyden, Fletcher, Goldfarb, Chanot method, the most popular quasi-Newton method, uses the following recursive formula to update the inverse Hessian approximation, this one. The first term ensures that the updated matrix satisfies the second condition. The second term removes an unnecessary curvature adjustment. And the final term introduces scaling factor xk, where the xk is bigger or equal 0, and at the same time less or equal 1. You can find it here. And this is stabilization parameter that controls how much of the update is incorporated. Several auxiliary terms appear in the formula. The first one, this is a correction vector vk, vk multiplied by vk transpose. This vector helps refine the inverse Hessian update. We can name this like correction vector. And scaling factor tau k. Tau k controls the step length adjustment. Initial approximation d0 is usually set to a positive definite matrix, definite matrix, sorry. The step size alpha is determined by line search to ensure sufficient descent. For quadratic functions, the final inverse Hessian approximation satisfies dn is equal inverse matrix Q. This means that after n iteration, the exact inverse Hessian is recovered. Summarizing this slide, I can tell that quasi-Newton methods approximate the inverse Hessian iteratively, avoiding expensive matrix computations. Curvature information is obtained using the difference between iterates and gradients. And the Broyden, Fletcher, Goldfarb, Chanot update formula ensures a stable, efficient update of the inverse Hessian. These methods converge much faster than gradient descent while using significantly less memory than Newton's method. Just to remind you, curvature information which we can take knowing the Hessian matrix form. Curvature describes how the gradient of the function changes as we move through the function domain. It's formally captured by the Hessian matrix, which contains second-order derivatives, partial derivatives in some definite direction. And if the Hessian is positive definite, the function is convex. If the Hessian has negative eigenvalues, the function has curvature in multiple directions. For sure, it will help us for better search directions, for faster convergence, and to avoid zigzagging. Additionally, let's consider some named non-derivative methods. And here we can cover 3 major numerical optimization techniques in general, finite different methods for approximated gradients, and coordinate descent, and direct search methods, so named Nonlinear methods. For example, for finite different methods, in optimization we often need the gradient nabla f by, but computing it analytically can be difficult or impossible. Instead, we use finite difference to approximate derivatives numerically. We can tell this about forward difference approximation is a small step size, and i.e. here there's a unit vector in the i's directions, and this method estimates the derivative by taking a small step forward in the i's direction, for example in x direction or in y direction here. Central difference approximation takes a step forward and backward to improve accuracy, reduces numerical errors, making it more accurate near convergence. You can see here this is a central difference in direction of x, central difference in direction of y. Forward difference are simpler but less accurate, and central difference are more precise but require twice the function evaluations. Use central differences when accuracy is critical, especially near convergence. Coordinate descent optimization. Instead of updating all variables simultaneously, coordinate descent optimizes one variable at a time while keeping other fixed. Advantages of this method: this efficient for high-dimensional problem since each step is computationally cheap, and works well with bound constraints where each variables has limits. For example, non-negative constraints. This diagram shows the optimization starting from xk, moving along one coordinate direction to xk plus 1, and then moving along other direction to xk plus 2, and so on. Successive steps lead to convergence. Such kind of methods, like non-derivative methods, they're good for high-dimensional problems where full gradient methods are expensive, handles constraints naturally by moving along one variable at a time, and however, it may converge slowly if variables are highly correlated. And a little bit about direct search method, Nonlinear methods. I just mentioned this here. Direct search optimization method that does not require gradients. Uses a simplex, a set of n plus 1 points in an n-dimensional space, expands, contracts, or reflects the simplex to find a better solution. And it's useful when gradients are unavailable or unreliable, for example, for noisy functions, and works well for non-differentiable and discontinuous functions. But it has some limitations, can be slow for high-dimensional problems, does not guarantee global convergence. Some short comparison of these non-derivative methods. For finite differences, it approximates gradients using function evaluations. For coordinate descent, optimizes one variable at time, can use gradients if available. And for Nelder-Mead methods, uses only function values, no gradients required. So according your uses, you can choose the appropriate methods for calculation. Thank you for attention. It was me. My name is Bahit Nurashevna Alipova. It was lesson about additional methods in framework of course methods for nonlinear programming for undergraduate students at the International IT University. And again, I have used open source Dmitry Bertseka's slides from MIT of the same course. Thank you for attention.